Hello, pandemic pre-calculus. Welcome back. In this video, I'm going to talk to you a little bit about something called the intermediate value theorem. But it's best for this to just start with a little brain twister. So I want you to think about this puzzle. I want to know if you can connect points A and B with a continuous line without crossing the x-axis. So here's our point A and here's our point B. So would you be able to touch a line that connects these 2 points? Well, this crosses the x-axis, so that wouldn't work. So is there any way to connect these 2 points without crossing the x-axis? Give yourself a second to think about it. Maybe sketch it, see if you can try a few. And it turns out you can't, no matter how I draw a line connecting A and B. If I draw a continuous line with no gaps, I'm always going to cross the x-axis at some point. Even if I did something like this, it would still cross the x-axis because this arrow here on my x-axis says that that x-axis continues off to infinity. So I would still be touching the x-axis right here. So it's not possible. And I would like you to take a second and think about why this is. Why is it that you can't connect A and B? What could you do to make it possible to connect A and B without touching the x-axis? You give up? Well, if you moved A or B, right, I could move A right up here. Now it's possible. But as long as A is below the x-axis and B is above the x-axis, if I draw any line that connects those two that's a continuous line, they're going to touch. That line is going to touch the x-axis. So it turns out that's the intermediate value theorem. When I have a polynomial function, goes from a negative value, I spelled goes wrong, goes from a negative value, like the point A in the example up here. It goes from a negative value to a positive one. It must cross the x-axis. So we have here, if I have a polynomial function with no gaps, no jumps, it's continuous, it's going to have to touch that x-axis at some point. And we can even get more precise than this little definition here. I can tell you this is a formal statement of the intermediate value theorem. So we have this intermediate value theorem I'll do in yellow. So this is the intermediate value theorem. Intermediate means in the middle of or in between. So these intermediate value theorem is talking about some value in between two other values. So this is what we have. So let's say we have a polynomial function f. Let f be a polynomial function. In our example that we did above, that polynomial function was the line we were connecting A and B with. And suppose we have this case. If f of A and f of B have opposite signs, one is positive, it's above the x-axis. The other is negative, it's below the x-axis. We have that case. There exists at least one value call it x is equal to c. There's some other point on the axis such that f of c is going to be equal to 0. That's going to be the x-intercept of our polynomial function that's in between a and b. That's where it crosses the x-axis. Let me do a quick example and then we'll wrap that up. We'll wrap this video right up. Let's do an example using the intermediate value theorem. So you use this often to show things, prove to somebody. So let's show that this function, f of x, is equal to x cubed. Oh, I didn't give myself nearly enough room. Show that f of x equals x cubed minus 5x squared plus 3x plus 6 has 2 real zeros between x equals 1 and x equals 4. We're going to use the intermediate value theorem to do this. When they say real zeros, that means places where we have x-intercepts. And so what we're looking at here is we're saying, look, I have some polynomial called f of x, and I have this graph. I'm going to give us an x and a y axis here. So here's our point, x is equal to 1. And here's our point, x is equal to 4. And I want to prove to you that somewhere in here, in that region, I'm going to touch the x-axis. So let's take a look. Here's how you could actually do this. We're going to go ahead and fill out a nice little table here with our x and our f of x values. And we're just going to go ahead and plug in 1, 2, 3, and 4 and get out our values. So go ahead and plug those into the function. Take a second and practice that. Plug those into this function here for x and fill in that table so that you can have the given values. You can go ahead and pause the video here and fill in that table. All right, so let's check your work and see how it went. So here are the values you get when you plug in those values into the function. So let's go ahead and actually plot those points on the graph, and you'll see how the intermediate value theorem works here. So at 1, I have the value 1, 5. I have this point here. At 2, the value 2, 0. Oh, that's one of the points we were looking for. At 3, I have negative 3. And at 4, I have positive 2. So I have some function here that connects all of these dots. And just like in the puzzle we had before, I have this dot above the x-axis, and this one below the x-axis, and this one again above the x-axis. And so what happens here is I have to cross once, and you know, we found one value where we cross. And then I have to cross at some point, I'm going to have to cross a second time so that my function can make its way back up and hit this dot here. And that's the intermediate value theorem. I hope that makes some sense to you. You know, bring me questions in class or talk about it on the discussion forums. And I hope that you are staying safe out there. And I'll see you in the next